In the next few parts, we'll look at multi-agent problems, otherwise known as games. By games, we don't mean digital games or board games like chess, although these are multi-agent games. By games, we have a more general term that describes a problem involving multiple agents. So far, we've assumed that there's just one agent that can affect the world in a Markov decision process. In multi-agent games, the rewards received and the states that we end up in depend on the actions of more than one player in a game. In this first part, we'll look at normal form games, which are single-shot games in which players play their actions simultaneously. We'll look at how to calculate the best response for an agent in a normal form game and how to construct strategies for normal form games. We'll study the concept of Nash equilibria, which is an important concept in games. After this section, you're expected to be able to identify situations in which normal form games are a suitable model for a problem, manually calculate the best response and Nash equilibria for two-player normal form games, compare and contrast pure strategies and mixed strategies in normal form games, and implement algorithms that can calculate strategies and Nash equilibria automatically for larger games. Let's get started. Consider the following, hopefully fictional scenario. You and your partner in crime have been arrested for armed robbery. To avoid a lengthy trial, the police put you and your partner in separate cells, unable to communicate with each other. The police offer you each the following deal. If both of you deny your guilt, you'll be charged with carrying illegal weapons and will receive 1 year each in prison. If one of you admits you're guilty, while the other doesn't, the prisoner that admitted will get off free in exchange for the confession, while the other prisoner will receive 4 years in prison. If you both admit you're guilty, you'll each receive 2 years in prison. The length is reduced from 4 years in exchange for your confession. Assuming that you care very little for your partner, you are an armed robber after all, what choice will you make? Will you cooperate with your partner in crime and deny your guilt, or will you betray your partner and admit your guilt? Remember, you have no idea which choice your partner will make, and you can't communicate. So what did you decide to do in the prisoner's dilemma? Did you decide to admit, or did you decide to deny? You might be surprised to know that the best thing you could do is admit, if your goal was to minimize the amount of time you spend in prison. Let's have a look at how we might solve this. We have two players, or two agents, in this game, and we're going to draw a matrix that shows the different outcomes that can happen depending on which action each player chooses. On the left, we'll have player 1. On the top, player 2. If we draw a matrix, we can specify the different moves that each player has. So you can see here we've got that player 1 can admit or deny, player 2 can admit or deny, and we have the 4 possible outcomes depending on which moves each player makes. If both players admit, they receive 2 years in prison each. I'm going to model this that they receive a reward, otherwise known as a payoff in game theory, of -2. So we can see here if they both admit in the cell, we have both receiving a reward of -2. In this notation, the element on the left refers to this player's payoff, and the element on the right refers to this player's payoff. If player 1 decides to admit and player 2 denies, player 1 gets off with no years in prison, while player 2 gets 4 years in prison, so we'll model this as -4. And the reverse holds if player 2 admits and player 1 denies. Finally, if both the players deny, they get 1 year in prison each. So we can see our game can be modeled in this matrix style. And we can model any two-player game like this in a matrix. So what's the answer to the prisoner's dilemma? Why should you admit if you're a prisoner? The way to solve this is to look at what you should do depending on the action of the other player. Let's assume that we are player 1. If player 2 decides to admit, what would be the best thing we could do? Let's have a look. If player 2 decides to admit, then we could either admit, which would receive 2 years in prison, or a payoff of -2, or we could deny and we'd receive 4 years in prison or a payoff of -4. -2 is larger than -4, so we should select to admit. Therefore, if player 2 admits, we should admit. However, we don't know whether player 2 is going to admit or not. They might deny. Let's think about what happens if player 2 denies. If player 2 denies, we could either admit and get off with no years in prison, or we could deny and get 1 year in prison. Well, 0 is greater than -1, so we should admit. So what this means is, no matter what player 2 does, player 1's best response to that is to admit. Therefore, player 2 should admit, because no matter what player 2 does, it's the best thing player 1 could do. This is known as a dominant strategy. It is the best strategy, irrelevant of what the other player does. We could reason about this from player 2's perspective as well. Because the game is completely symmetric in this case, we would see the same thing. The best response for player 2, if player 1 admits, is to also admit, because they would rather get 2 years in prison than 4. And player 2's best response, if player 1 denies, would be to admit as well. They would prefer to get no years in prison than -1. So both of these players end up admitting their guilt. You can see now why this is called a prisoner's dilemma. It's called this because there is actually a better outcome for both players if they both denied. If both the players could deny, they would get 1 year in prison instead of 2. However, from an individual perspective, they're both better off admitting. So even though globally there's a more optimal solution, both players individually have an incentive to admit. Thus, this is the dilemma. So this is an example of a normal form game. Normal form games are these games that we can draw in matrices like this. In a normal form game, there are a few important concepts that we need to know about. First of all, there's a set of players. There's only 2 players in this game, the 2 prisoners, but in other games there can be more than 2 players. There's also an action profile, where each agent has a set of actions that are available to them. In this case, they both have the same actions, they can either admit or deny. Again, we can have multiple actions rather than just 2, and the 2 players can have different actions to each other. There's also a reward or a payoff for each player, which are our elements in the cell here. We sometimes call this the utility of this outcome. So unlike a Markov decision process, the reward or the payoff received by each player depends on what other agents in the environment do as well. When we choose admit, we don't know what our payoff will be in advance because the outcome depends on what the other player does. So when player 1 admits, they can get either 2 years in prison or no years in prison, and it depends on the choice of the other player. This is what distinguishes games from Markov decision processes. In games, we have to be strategic about the selection we make and consider the possible actions of the other agents when we make our decision. Formally, a normal form game, G, is a tuple with 3 components. N, number of agents that are in the environment. A, which is a set of action profiles available to the agents. And U, which is a utility function that defines the payoffs for each agent. N is simply a number that defines the number of agents. A is a set of action profiles, 1 for each agent. And the set A is a cross product of each of these. We can describe an individual action profile, A1, AN, which are the tuple of actions from all agents in a game. And U, the utility function, is a mapping from an action profile to a tuple of n real numbers. This tuple specifies the payoff that each player receives if the agents play this action profile. Thus, this is called the utility, so we give it the letter U. There's some assumptions that are made when we're talking about game theory. The first is that all players are rational. What this means is that all the players are trying to maximize their utility. And from the perspective of each player, they each assume that all the other agents are able to calculate this optimally. The second assumption is that agents are self-interested. This just means that they don't worry about the payoffs of other agents. They're only interested in maximizing their own utility. In the concept of the prisoner's dilemma that we see here, the two players don't care about the other player minimizing the amount of time in prison, like two people might do. So in this case, we say that they're self-interested. The third assumption is that players have perfect information. This just simply means that all the players know all the information about the game. They know the actions that are available to them and each other. They know the number of agents that are in the environment, and they all know the payoffs. This is all common knowledge between all of the players. And in a normal form game, we assume that all moves are simultaneous. This just simply means that each player has to submit their move without seeing the move of all the other agents. The moves might not necessarily be simultaneous. Player 1 can submit their move before player 2, but from their perspective they're simultaneous because they don't know or see which action player 2 is going to take. Now let's look at how to solve games from the perspective of one of the agents. The best response for an agent, I, if its opponents play a certain strategy, is a strategy in which the utility is better than all the other strategies that it could play. So let's just analyze this in a two-player game, but the idea generalizes to multiplayer games as well. If agent I plays a strategy, which we'll call S star of I, then we can say that the utility of that strategy, given the other player's strategy Sj, is defined like this. U of I for strategy Si if agent J plays strategy Sj. If the utility of that strategy is greater than or equal to the utility of S prime I against the strategy Sj for all Si prime, then we say that this is the best response that agent I could play to strategy Sj. Let's pause and analyze this for a second before we go on. What this says is that if agent J plays strategy Sj, that is, if we know which strategy the other agent is going to play in advance, then the best response for this is the strategy that maximizes our utility. In other words, it is the one with the utility that is greater than or equal to the utility of any other strategy agent I could play. For some problems, there are multiple best responses that could be played. The utility of them is the same as each other. Using this definition of best response, we can define the Nash equilibrium of a game. The Nash equilibrium is named after the famous mathematician John Nash, who in his PhD thesis showed that all finite normal form games have a Nash equilibrium. We say that the strategy profile S is a Nash equilibrium if for all agents I And for all strategies, SI, in this strategy profile, SI is a best response. So let's just pause and analyze these two concepts again. If agent J, or all of the other agents, pick a certain strategy profile, then the best response to that strategy profile is the strategy that maximizes the utility. This assumes that we know in advance which strategy profile agent J is going to select. If we know that, we can define a best response. The Nash equilibrium is a strategy profile for all agents such that each of these is a best response to each other. In other words, what that means is each of these strategy profiles here is the best response individually for that agent, assuming all the other agents play the strategy that's in this profile. Let's have a look at this concept in the prisoner's dilemma over here on the right. We already know that admit is the best response for both agents in the game. The Nash equilibrium is therefore this pair, admit, admit. That is a strategy profile that's a Nash equilibrium. We can verify this in these normal form games by looking at each cell and seeing if that is the best response for each agent in that cell. Let's have a look at the prisoner's dilemma and decide whether this cell down the bottom is a Nash equilibrium. In this situation, where they both deny, is this a Nash equilibrium? It's not, because we can see that this isn't the best response for player 1 if player 2 denies. Player 1 has an incentive to deviate and play admit instead. Therefore, this is not the best response for agent 1. Similarly, it's not the best response for agent 2, so this is not a Nash equilibrium. Similarly, in this cell, this is the best response for player 2. By changing their action, they could only get worse, 1 year in prison instead of 0. But it's not the best response for player 1. They have an incentive to deviate by admitting because they can get 2 years fewer in jail. So let's have a look at the answer that we do know is a Nash equilibrium here. Is this Nash equilibrium? It is, because no player has an incentive to deviate from this. This is the best response for both players. If player 1 deviated from this strategy profile, they would get more years in prison. And similarly, if player 2 deviated, they would get more years in prison. Therefore, neither player has an incentive to deviate. And this is our Nash equilibrium of the game. A final concept that's important is a concept of a dominant strategy. We say a strategy is dominant if it's the best response to all the possible strategies our opponent can play. A strategy S star I is a dominant strategy for player I if for all the strategies of our opponents the utility of that strategy is higher than all the strategies available. We say that a strategy is weakly dominant if the utility is greater than or equal to all the other possible strategies that are available. And we say that a strategy is strongly dominant if it's strictly greater than all the other possible strategies available to the agent. In the prisoner's dilemma, admit is a strongly dominant strategy for both agents. This is because, irrelevant of what the other agent does, admit is always a higher utility than deny. Now let's do an exercise on a game called the advertising game. In the advertising game, we have two firms, firm 1 and firm 2, and they each have to decide whether they're going to advertise in order to generate new business for themselves, which will take business away from each other. They can either not advertise or they can advertise. The payoffs in this game aren't symmetric because the two firms are different sizes and therefore they get different advantages for choosing to advertise. If neither firm advertises, then firm 1 gets a payoff of 16. We could say this is, for example, $16,000 per month that they earn in revenue that month. Firm 2 would get a payoff of 12. On the other hand, if firm 2 decides not to advertise but firm 1 does, then firm 1 will take some business away from firm 2, but its payoff will go down because the amount of business it gets is not enough to cover the advertising costs. On the other hand, if firm 2 decides to advertise and firm 1 doesn't, then it takes business away from firm 2, but also it gains so much business that its overall profit increases because the amount of business it gains is more than the advertising cost. If they both choose to advertise, then their payoffs are 6 each. So the payoff goes down for each of them because the cost of the advertising is high, but they don't gain any new customers if they each advertise. Your job is to solve this game. Do the players have dominant strategies? If yes, what are they? If no, why not? Is there a Nash equilibrium in this game? Try solving this and see what your answer is. So how did you go? Did you solve the game? Well, let's have a look at the answer. For firm 1, there's clearly a dominant strategy. If firm 2 chooses not to advertise, then clearly firm 1 should not advertise because it gets a higher revenue, payoff of 16 instead of 13. Similarly, if firm 2 chooses to advertise, firm 1's payoff for not advertising is 7 versus 6. So this is a dominant strategy for firm 1. Does firm 2 have a dominant strategy? Well, we can see here that if firm 1 chooses not to advertise, firm 2 should advertise because it gets a slightly higher payoff. But if firm 1 does choose to advertise, firm 2 would not advertise because it gets a slightly higher payoff for that. So there's no clearly dominant strategy here. However, what firm 2 can do is reason about what firm 1 would do. If firm 2 assumes that firm 1 is rational and self-interested, which, as you recall, is one of the assumptions of normal form games, it would reason that firm 1 is going to choose do not advertise because it's a dominant strategy. So firm 2 can effectively eliminate this row of the game. Then it just becomes a game with one action available to firm 1, do not advertise, in which case firm 2 can choose to advertise. This is the best response for do not advertise, and therefore it's a strategy that firm 2 should play. It's strictly not a dominant strategy because a dominant strategy has to be the best response for all possible actions. However, it is a dominant strategy to all the feasible strategies that firm 1 would take, assuming it was rational and self-interested. So given firm 2's best response of advertising, we can now quite easily calculate what the Nash equilibrium is, which is this cell here. We can always eliminate these rows or columns in a game when a strategy for an agent is dominated by the other strategies. We say that a strategy is dominated if it's never the best response for any of the strategies of the other agent. We can effectively ignore those rows because we know the other agent will never play them. So in the advertising game, we can see that we have this as a Nash equilibrium. Let's quickly verify that to confirm to ourselves that it is a Nash equilibrium. If we're in this cell, does firm 1 have any incentive to deviate? Now we've already decided that that's a dominant strategy, so by deviating their payoff goes down from 7 to 6. Does firm 2 have any incentive to deviate? No, because their only payoff will go from 13 down to 12 if they do this. Therefore this is a Nash equilibrium for the advertising game. Let's do one more exercise known as the split or steal game. In the split or steal game, we can assume that there's two players and they each have access to a possible prize money that they could win. But the two players have to make a decision. Will they split the prize money, or will one of them try and steal it off the other? If both players split the prize money, they share the prize money, which we model as them getting a payoff each of 1. On the other hand, if one player decides to split the prize money and the other decides to steal it, the one who steals it gets all of the prize money and the one who decides to split it gets none, and vice versa. Finally, if both the players decide to steal, they each go away with nothing. Do either of the players have a dominant strategy in this game? If yes, what is it? Are there Nash equilibria in this game? If yes, what are they? How did you go? Did you find out if there's a dominant strategy? Let's have a look. We can analyze just one player because the game's completely symmetrical, so it will be the same for either player. If we're player 2 and player 1 decides to split, our best response is to steal. We'd get a payoff of 2 instead of 1. If player 1 decides to steal, then our best response is neither split nor steal because the utility is the same. Therefore, in this game, we say that both players have a weakly dominant strategy of stealing. So what's going to be the Nash equilibria for this game? Well, clearly, if we have a weakly dominant strategy, we can say that this is going to be a Nash equilibrium. Does player 2 have an incentive to deviate? No. They can only get the same payoff if they deviated. What about player 1? Do they have an incentive to deviate? No, they can only get the same incentive to deviate. Therefore, this is a Nash equilibrium. However, there are multiple Nash equilibria in this game. Let's look at this one here. Does player 2 have an incentive to deviate from this? No, if they decide to split instead of steal, they get a payoff of 1 instead of 2. Player 1 also has no incentive to deviate because their incentive will remain the same. Therefore, this is a Nash equilibria. And because it's a symmetric game, we know that this is also going to be a Nash equilibria where no player has an incentive to deviate. In this game, despite the fact that we have weakly dominant strategies, we have multiple equilibria in the game. This is because the strategies are only weakly dominant. Therefore, in games where both players do not have a strongly dominant strategy, we can have multiple Nash equilibria. Now let's have a look at a game that has a slightly different structure to the games we've seen so far. It's still a 2-player normal form game with 2 moves each, but you'll see in a minute why it's a bit unusual compared to what we've seen so far. The game is called Matching Pennies. In this game, there's 2 players, player even and player odd. They both have to choose heads or tails. If both the players choose heads, or both the players choose tails, we say that the outcome of the game is even. If one of the players chooses a head and one of the players chooses a tail, we say the outcome of the game is odd. If the outcome of the game is even, then the even player gets a payoff of 1, while the odd player gets a payoff of -1. And if the outcome of the game is odd, then the odd player gets a payoff of 1, and the even player gets a payoff of -1. Let's have a look why this is a different game to what we've seen so far. Does player even have a dominant strategy? Well, if player odd plays heads, the best response for player even is to play heads. But if player odd plays tails, the best response is to play tails. No dominant strategy there. And we see similarly that for player odd, if player even plays heads, the best response is tails. And if player even plays tails, the best response is heads. No dominant strategy there. How do we think we're going to solve this game then if neither player has a dominant strategy? Well, we could look at Nash equilibria again. But we'll see that Nash equilibria don't really exist, at least not in the way that we've been describing them so far. With a Nash equilibrium, in each game, one of the players has an incentive to deviate. If we think about this cell here, player odd has an incentive to deviate by changing from tails to heads. In this one here, player even has an incentive by changing from tails to heads, etc. This is because so far we've been discussing pure strategies and pure equilibria. By pure, we mean that the strategies consist of the actions that are available, heads or tails. In the next part, we're going to look at so-called mixed strategies. Mixed strategies are strategies in which we play the different actions according to some probability distribution. In other words, we would play heads with some probability and tails with some probability. The key challenge in these types of games is to determine which probabilities should we use for those. A key concept in solving these types of games is the concept of expected utility. Expected utility is the weighted average that we receive by playing a particular pure strategy. Formally, we define the expected utility capital U for player I, of playing an action A as follows. In other words, the expected utility to agent I of playing an action A is the sum of playing that action against all of the possible actions that our opponent can play, multiplied by the probabilities that our opponents will play those actions. In theory, we can maximize our overall utility by picking the pure strategy with the highest expected utility. However, in a real game, we do not know what the probability our opponents will play these moves. This is where the concept of expected utility becomes useful when we define the idea of indifference. The concept of indifference is important when we're solving games with no dominant pure strategies and no pure Nash equilibria. We say that an agent I is indifferent between strategies AI and AJ if in other words, for two strategies AI and AJ that are available to agent I, the agent is indifferent between those if the expected utility of these is the same. So what we've got here is two pure strategies or actions, and agent I is indifferent between those if the expected utility is the same. We don't know though what the expected utility of an action is if we don't know the probabilities that our opponents will choose it. Next, we're going to look at how we can calculate strategies and how we can calculate Nash equilibria using this idea of indifference as applied to both players. So now let's define the idea of a mixed strategy Nash equilibria. This is an equilibria where the two players play a mixed strategy, which means that they probabilistically choose the action that they're going to play in a game. A mixed strategy for an agent, which we'll call SI, is a vector of probabilities P1 to Pm for each of the M actions that are available to that agent, such that the sum of all those probabilities equals 1. So therefore we have a probability, 1 for each pure strategy or each action that's available to an opponent. Well, I guess intuitively we want to select the probabilities such that they maximize our expected utility. However, remember the expected utility relies on these probabilities for the other agents in our game, which we don't know. So this may seem a bit strange. We select our probabilities not to maximize our own payoff, but to make our opponent indifferent between the different pure strategies that they have. However, if we analyze this from the perspective of the opponent, it becomes clear. If the opponent, say, had two possible pure strategies to choose from, action 1 and action 2, and we selected our probabilities such that these weren't indifferent, for example, the expected utility for agent J was higher for A1 than it was for A2, we then give an incentive for agent J to play pure strategy A1. This means that at least one strategy has a higher expected utility. In that case, they would play that action every time. If we give an agent some strategy in order to play this, then we're giving them some advantage. Instead, the best thing to do is to select our probabilities such that when they look at the difference between A1 and A2, it doesn't matter which one they choose. They may as well choose either of them. So this idea of indifference becomes important for calculating the best mixed strategy for an agent in a normal form game. but importantly, we select the probabilities of our strategy such that it makes our opponent indifferent between the different actions in their action profile. A mixed strategy equilibria is the combination of all the best strategies of each agent in a game. So it would be the strategy for agent 1, agent 2, up to agent n, where each one of these strategies is a mixed strategy that assigns a probability to the underlying actions in the game for every agent. So let's apply this idea of indifference to calculate a mixed strategy and a mixed strategy equilibria for the matching pennies game. I think we'd agree that without even solving it, it's reasonably intuitive that what we should be doing is selecting heads with probability 0.5 and tails with probability 0.5. But let's see if we can solve this analytically to get that answer. So let's solve for player odd. For player odd, they need to choose the probability of heads and tails to make player even indifferent between its own actions. Player even. So if the utility function u even is the utility that player even gets for playing heads and for playing tails, we need to set the probabilities of our actions in order such that these two expressions are equal. So let's set the strategy profile for agent odd to be y1 minus y, where y is the probability that odd plays heads and 1 minus y is the probability that odd plays tails. Y is the probability that odd plays heads and 1 minus y is the probability that y plays tails. We can now specify a constraint for what the expected utility of even is for playing heads. Let's define what this expression would be. So if even played strategy heads, then the expected utility would be y, which is the probability of player odd playing heads, multiplied by the outcome even would receive, which is 1, plus 1 minus y times the outcome that even would receive for playing heads, which is minus 1. Therefore, this would be 1y plus minus 1, this outcome, times 1 minus y would be the expected utility of playing heads. Similarly, we can find the expected utility of playing tails, which would be y times minus 1 plus 1 minus y times 1, which is 1. So all we need to do now is solve for y in this inequality, and we'll get the probability that player odd should play the action heads. So if we simplify this here, we get 2y minus 1, and if we simplify this right hand side, we get 1 minus 2y. And we can bring the y over to both sides and this coefficient here over to both sides, so we can get 4y equals 2, and now we can move the 4 over to the other side. We get y is equal to 2 on 4, and therefore y is equal to half. So now we have that if agent odd plays the action heads with probability of half, and therefore the action tails with probability 1 minus half, which is half, then this is their best strategy in this game. So for odd, the strategy would be half, half. If we solve for player even, we'd simply find the same answer because this is a completely symmetrical game. So let's recap what we've done here. We have assigned the variable y to be the probability of playing heads, and therefore 1 minus y the probability of playing tails. By assigning those, it's allowed us to figure out what the expression would be, that is the expected utility for player even if they played heads, and also the expected utility for player even if they played tails. Taking these expressions and making the player even indifferent to those, we solve for y, and we get that the probability of playing heads should be half and the probability of playing tails should be half. If both of these players play with probability half, they make each other indifferent to their own strategy. And therefore the mixed strategy equilibria is player odd playing with probability half and half, and player even playing with probability half and half. Now, let's look at a slightly more involved game. On the screen here we have what's called a security game, where we have a defender that's defending some assets from an adversary. In this example, the defender is trying to defend two airport terminals, Terminal 1 and 2. The adversary is trying to attack the same two terminals. However, both players value the terminals differently to each other, and they each value each terminal differently to the other terminal. So for example, if the defender successfully defends an attack on Terminal 1, it gets a payoff of 5, whereas if it successfully defends a payoff of Terminal 2, it gets a payoff of 2. Similarly, if the adversary successfully attacks Terminal 1, it gets a payoff of 5, and if it successfully attacks Terminal 2, a payoff of 1. So this models the fact that each of them values the terminal differently to each other and each terminal differently. So therefore the probabilities of how to make each other indifferent are a little bit more involved. First, why don't you have a go to see if you can calculate the two mixed strategies, the one for the defender and one for the adversary, which will give you the Nash equilibrium for this game. So let's assign y the probability the adversary attacks Terminal 1, and 1 minus y the probability they attack Terminal 2. To make the defender indifferent, we want the utility for the defender of defending Terminal 1 to be equal to the utility of defending Terminal 2. This expression will be y times 5 plus minus 1 times 1 minus y. And this expression will be minus 5 times y, 2 times 1 minus y. We can simplify this left side to 6y minus 1, and the right hand side 2 minus 7y. We can now move the y's to the same side, which just simplifies to y equals 3 on 13. So therefore, the mixed strategy for the adversary that makes the defender indifferent between defending Terminal 1 and Terminal 2 would be 3 on 13 and 10 on 13 for Terminal 1 and Terminal 2 respectively. Now we want to calculate the mixed strategy for the attacker, which will give us our equilibrium. So for the attacker, it's the same kind of deal. We're going to give probability of x of defender defending Terminal 1 and 1 minus x defending Terminal 2. If we want to make the attacker indifferent between attacking both of these, then we need to make the expected utility the same over each of these. The expected return of attacking Terminal 1 would be minus 3 times x plus 5 times 1 minus x. The expected return of attacking Terminal 2 would be 1 times x plus minus 1 times 1 minus x. If we simplify these expressions, like so, we can then factor the x onto the same side. Therefore x is equal to 6/10 or 3/5. And the strategy for the defender becomes 3/5 terminal 1, 2/5 terminal 2. So therefore, the Nash equilibrium of this game would be the strategy profile where the adversary attacks terminal 1 with probability 3/13 and terminal 2 10/13, and the defender defends terminal 1 with probability 3/5 of 2/5. These two strategies that make up the equilibrium are the two strategies that make each player indifferent to the actions of the other. The security game we saw earlier is just a simplification of the real security games that people use game theory to solve. For example, the research group led by Professor Milantambe at Harvard University uses game theory in order to solve problems such as defending terrorist attacks and searching for poachers in African and Southeast Asian wildlife areas. Those games are at much larger scale and are a slightly different type of game than what we've studied in this subject. In those real games, we have normal form games such as earlier, where we have a defender trying to defend some targets and an attacker potentially trying to attack them. However, unlike in the earlier games, we're not sure how much the attacker values different targets. We model this using what's known as a Bayesian-Stackelberg game. In these games, the adversary or the attacker might value our targets different depending on what type of adversary they are. We model this as a Bayesian game where we have one game that's of probability 0.3 occurring and another game that's a probability of 0.7 occurring. The difference between these two games is that our adversary values terminal 1 and terminal 2 differently. For example, in the left game, our adversary values a successful attack on terminal 1 as 5, whereas they only value it as 2 in this game. And in the left game, they value a successful attack on terminal 2 as 1, whereas they value it in 3 in this game. This is to model uncertainty into how much our adversary values the different terminals. This is a payoff we don't know. By assigning probabilities to a range of different adversaries, we get a range of different games that we have to solve. The complication in these Bayesian games is that we have to choose a mixed strategy to defend terminal 1 and terminal 2 without knowing the actual payoffs that our adversary may have. What we have to do is maximize our expected utility based not just on the payoffs, but also the probability that our adversary values these terminals as different values. Professor Tambe's group uses game theory to solve this. However, they solve massive scale games where there are a lot of actions available to each player. They have to use advanced optimization techniques in order to, for example, eliminate some rows and columns for the game to make it more computationally feasible to solve. They've applied these techniques successfully to a range of different application areas, one being ticket inspection on the LA Underground network, another being defending ferries in New York Harbor from potential terrorist attacks. We can see an example here where the Coast Guard boat that's defending a ferry randomly is assigned a strategy to switch ferries in the middle of a patrol. This is successfully using mixed strategies where the probabilities are randomized to help catch out the potential adversaries. Perhaps more impressively, they've used these game theories techniques to catch poachers in Africa and in Southeast Asia. Because poaching is such a huge problem, and there are very few rangers compared to poachers and a very large area to patrol, using mixed strategies with potential randomization makes it very difficult for poachers to avoid park rangers when they're trying to poach animals. They use a range of artificial intelligence techniques, including game theory, in order to generate schedules for rangers to go out and survey wildlife areas. In this part, we introduced the notion of normal form games. These are multiplayer games where players have to play actions at the same time. We looked at several important concepts of multiplayer games. strategies, including weakly and strongly dominant strategies. We looked at pure strategies, and we looked at mixed strategies, where you play pure strategies to some probability distribution. We learned how to calculate the best response for an agent, and how this can be used to further calculate the Nash equilibria of normal form games. And we learned how to calculate mixed strategies to make our opponent indifferent to our actions. In the next part, we'll look at sequential move games, which are multi-agent Markov decision processes, where agents take turns in making moves rather than moving simultaneously. So stay tuned.